All right, welcome back. We're going to talk more about the two-sample t-test, and we're going to give another example and just show, like we showed in other situations, namely confidence intervals for single mean and the paired t-test, that when we have smaller samples, we need to change the mechanics slightly, but the basic concepts remain in place. So we'll give another example here with a smaller set of data than the last one. So in smaller samples, what is the sampling distribution of the difference in sample means? In larger samples, it's normal, but we'll use a generic rule here. If either or both sample sizes are less than 60, we have to be a little more conservative, and we'll use a t-distribution with n1 plus n2 minus 2 degrees of freedom. In other words, we go to a t-distribution which is uniquely defined by its degrees of freedom, and we take the total sample size across the two samples, and then we subtract 2. It's really the degrees of freedom for each of the two groups, n1 minus 1 plus n2 minus 1, which gives us this total. So this just means the same principles apply for getting a confidence interval and a p-value, but the distribution we use is slightly different. So for example, we'll have to go out slightly more than 2 standard errors to get 95% coverage in a confidence interval if our samples are small. So here's an example. In a randomized design, 23 patients with hyperlipidemia, that's high cholesterol, were randomized to take either treatment A or treatment B for 12 weeks. 12 patients were randomly assigned to treatment A, 11 patients to treatment B. LDL cholesterol levels in millimoles per liter were measured in each subject at baseline and at 12 weeks after the start of the study. And the 12-week change in LDL cholesterol was completed for each subject. So here we have another study, and not all two-sample comparisons are like this, where we first measure a paired comparison on members in each of the two independent samples, a before-after measure, and then what we're ultimately interested in doing is comparing that before-after measure between the two independent groups, those on treatment A and those on treatment B. And here's a summary of the results. In treatment group A, there were 12 subjects. On average, the 12-week change cholesterol level post-treatment less pre-treatment was negative 1.4 millimoles per liter. And in the treatment B group, that change on average was negative 0.32 millimoles per liter. So on average, both samples lowered their cholesterol level, but the decrease was greater in sample A. And then we have the standard deviations there for both groups. So the scientific question here was, is there a difference in the LDL change between the two treatment groups? So how can we approach this? Well, we can create a confidence interval for the difference in average LDL cholesterol level between the two groups, and we can do a statistical hypothesis test to get a corresponding p-value. So how do we get a 95% confidence interval? Well, the general formula, large samples, would be to take the observed difference in sample means and add and subtract 2 estimated standard errors of this difference in sample means. The general formula for smaller samples is almost identical, except how far we go is determined by our degrees of freedom. So we take the value that cuts off 95% in the middle of the t-distribution with n1 plus n2 minus 2 degrees of freedom. So generically, that means in really small samples, we'll have to go slightly greater than 2. But conceptually, it's the same exact idea. So let's see what we have here. The difference in sample means treatment A compared to treatment B is negative 1.41 minus negative 0.32, or a difference of negative 1.09 millimoles per liter. And the estimated standard error, if you go through the math, turns out to be about 0.25 millimoles per liter. So if we want to create a confidence interval for the difference in means, well, how many standard errors do we need to add and subtract to get 95% coverage? Well, since the sample sizes are small, we might have to add slightly more than 2 standard errors. And the number we need to add and subtract for 95% confidence comes from a t-distribution with n1 plus n2 minus 2, or 12 plus 11 minus 2, or 21 degrees of freedom. If you look this up in a t-table, the value we need is 2.08, so a little more than 2. And we'll show that you won't need a t-table in real life. We'll show in a minute that Stata will take care of this. But for computational purposes, this is the 95% confidence interval for the true mean difference in the change in LDL cholesterol level for the population of persons on drug A the population of patients with hyperlipidemia on drug B would be take negative 1.09 plus or minus 2.08 times that estimated standard error. It gives a confidence interval for the mean difference of negative 1.6 to negative 0.57 millimoles per liter. Notice that 0 is not in that confidence interval. This is a confidence interval for the difference in mean change between the two grub groups, so they suggest that there's a statistically significant difference after accounting for sampling variability. But let's take the p-value approach to complement this. We want to do a two-sample unpaired t-test, and we want to get a p-value. So from a hypothesis testing, we're asking the same question, slightly different phrasing, asking is the change in LDL cholesterol level on average the same in the two treatment groups? So our null here is the same as what we saw before, that the mean changes are the same, or that the difference in these mean changes is 0. So we employ our same general recipe. Start by assuming the null is true. There's no association, i.e. no mean difference in the change, treatment A to treatment B. We measure the distance of our sample mean difference from that null of 0, and then we compare this distance to the appropriate distribution to get a p-value. And in our case, if we go through the math of computing the standardized distance, we take our observed mean difference of negative 1.09, divide by the units in the standard error, 0.25 millimoles per liter. We get a result that's negative 4.4. Its distance is negative 4.4. So our study result was 4.4 standard errors below the mean of 0. 4.4 standard errors less than the expected mean difference in cholesterol change between the two treatments if our null was true. So as a result, 4.4 standard errors below 0 unusual? Well, it depends on what kind of distribution we're dealing with. The p-value, again, is the probability of getting a distance as or more extreme than what we observe by chance alone. In other words, getting something as far or farther away than 4.4 standard errors. This p-value comes from the sampling distribution of the difference in two sample means. What is the sampling distribution? Well, we already used it once to get the confidence interval. It's the t-distribution with 21 degrees of freedom. So what we're looking at computing here is the probability of being 4.4 or more standard errors away from 0 on a t-distribution with 21 degrees of freedom. That red area highlighted. Here's a t-curve with 21 degrees of freedom, and we're looking at that area in the tails. Again, could look it up in a t-table. That's really not that much fun. We'll go to Stata. It'll do everything for us. Same exact command as we used before, t-test I, and then the sample statistics from each sample respectively, and then comma unequal. And if you do that here, for this example, we get that confidence interval from negative 1.6 to negative 0.57 that we showed by hand, but we get it here, so that's nice. And we also get a p-value for this. Something 4.4 standard errors away from the center of any symmetric distribution, even if it's a t-distribution, is going to be rather unlikely. And here the p-value. If that were a normal curve, we know we're way off in the tails. And the same thing goes for t-distribution with 21 degrees of freedom. And that p-value here is 0.0003, so well less than the standard cutoff of 0.05. So if we were to write this up, we might say 23 patients with hyperlipidemia were randomly assigned to one of two treatment groups, treatment A or treatment B. 12 patients were assigned to receive treatment A. 11 patients were assigned to receive treatment B. Baseline LDL cholesterol measurements were taken on each subject, and LDL was again measured after 12 weeks of treatment. This change in LDL cholesterol level was computed for each subject. The mean LDL changes in the two treatment groups were compared using an unpaired t-test, and a 95% confidence interval was constructed for the difference in mean LDL changes. Patients on treatment A showed a decrease in LDL cholesterol level of 1.41 millimoles per liter, and subjects on treatment B showed a decrease of 0.32 millimoles per liter. And this is a difference in changes of 1.09 millimoles per liter on average, a confidence interval of 0.57 to 1.61. So I was changing the sign here, and instead of reporting these as negative, reporting them as decreases. You can do that instead of reporting the negatives if you like. And the difference in LDL changes was statistically significant with a p-value of less than 0.01, which we already know, that it would come in at less than 0.05 since our 95% confidence interval did not include 0.